Hello everyone. In this video we're going to discuss what is chemistry as well as the workings behind the scientific method. So if you were to define chemistry, you could say that chemistry is sometimes referred to as the quote central science. The central science is how we can describe it because if you look at a lot of other disciplines of science, you find that a lot of them interconnect back to chemistry. So, if you're considering entering a career such as environmental science or agriculture or some forms of biology or toxicology, CSI, things like that, even computer science, for example, those all have some sort of link to chemistry. In chemistry, we practice quite a bit of mathematics. We also have some connections to physics as well. So you'll find that chemistry has a lot of overlap. So by acquiring a mastery of chemistry, it is extremely useful for many STEM and other careers that you might pursue after taking this course. And in addition to that, chemistry also allows us to consider critical thinking skill, which is essential in really any line of work that you do. It's not just knowing definitions and vocabulary, but it's knowing that you have a set of tools that you can use. It could be formulas or definitions or other things like that. And how can you apply those tools to a unique situation or a unique problem? It's something that no matter what you do, you're going to have to be familiar with. If you go into sales or law or obviously STEM careers like medicine or things like that, even if you go into a trade, if you're a carpenter or a plumber or an electrician, you're going to have to do some problem solving, and it's very likely that you'll have to use some amount of critical thinking. So it's good for us to study chemistry, not just for the actual material, but also for these essential critical thinking skills. It just makes you a better citizen. If we were to define chemistry, like actually define it, it's the study of composition, properties, and interactions of matter. So all of chemistry revolves around how matter exists and really how matter changes, and kind of discussing the different types of changes that matter undergoes. So how do we study chemistry? So we know what it is, but the question, how, plays a major role in labs and in kind of understanding how chemistry has developed over time. And I know that many of you have heard of the scientific method before, right? But I think what students often get confused by is that the scientific method has a point A and it goes through a series of steps, and after we do those 4 or 5 or 6 steps or whatever, we end up at point B. And that's not necessarily the case with the scientific method. What we find is that the scientific method often is very cyclical, and you'll find that you might get to a certain point in the method, but then you can't continue further. You might have to work backwards or things like that. So if we were to kind of relate the scientific method to chemistry, we know that we have to make some sort of observation and we have to do some sort of experimentation in order to deepen knowledge of chemistry and in order to solve chemistry problems. Pharmaceutical companies have to utilize the scientific method when they're trying to do drug design and things like that. So the scientific method follows a process similar to the one below. This is generally considered to be your first step. It's identifying an observation and some sort of curiosity. So maybe you identify some problem or some lack of knowledge and you want to pursue it, and you have some ideas that might pertain to it, and you have this driving curiosity to solve those problems. So this is essentially the first step. It's kind of the beginning phases. Once you decide that, okay, I've seen this observation, I'm curious as to what it means or how it works, then we pursue our next step, which is generally forming hypotheses and making predictions. I believe that this is going to happen because of this, or I think this might work. Okay, so this is generally where we go after that. After that, You design and perform an experiment to make more observations because maybe the observation you made initially isn't deep enough, or maybe that curiosity you have needs something to support it. So you'll design an experiment and perform an experiment, and as a result of that, you generally collect data. Now, experiments can look differently based on what you're studying. In computational chemistry, for example, performing an experiment doesn't really deal with wet chemicals. Often you're using computer software to develop molecules and seeing how things change. So keep in mind, experiments look differently based on what you're studying. After those experiments are done, you make more observations. Then from that point, you have a choice based on the results. Let's say the results are not consistent with your prediction. Let's say I designed an experiment and it did not go well. Maybe the data didn't come out cleanly, or maybe there was an error in the methods for how the experiment was performed, or maybe we just got something that was totally out of bounds and it doesn't link up with our prediction. If that's the case, then we have to go back and think about our predictions, or think about, well, how do I design a better experiment? So that's usually what happens if things don't work. If your things do work, then you have some pieces where you can, kind of contribute to the literature, or you can contribute to the body of knowledge. So if you find results that, really do a good role, we first want to check and make sure they're replicable. So if things can be replicable, that's huge, because if you do an experiment one time and that's the only time you get those results, maybe you got those results as a result of an error or something along those lines. So we have to make sure that our experiments are replicable. Once they're replicable, we can contribute to the body of knowledge, and often scientists will publish their results in a scientific journal or other database for, the knowledge to be spread around the chemistry community. Now, once you have that body of knowledge contribution, you can have that hypothesis become a theory. And it can become a theory because, you need more additional testing, you need more results to support your hypothesis. Or if you do more and more and more testing over time, or more and more experiments, and you consistently see the same observation over and over and over again, that's when you get a law. And there's a pretty big difference between a theory and a law, and we'll get to that later on. So, when we do experiments, we have observations that can take two categories. They can be qualitative in nature, or they can be quantitative in nature. Okay? When we describe something as being qualitative, that means they deal with observable characteristics. So with qualitative things, again, the root word here is quality. So we're going to think about the 5 senses here with regards to qualitative observations. So if you think of your 5 senses, we have taste, we have touch, we have hear, we have smell, and we have sight, right? So all those. So with your 5 senses, what are you seeing? Do we see a color change? Do I hear some fizzing? Is there a unique smell being released? Is the beaker or the reaction vessel getting hot? Is it getting cold? Is it, creating a gas or creating bubbles? These are the types of observations that are qualitative in nature. When we deal with quantitative observations, that means your observation is dealing with some amount of numbers. So if I do an experiment and I get some white powder, well, how much does that white powder weigh? If I were to, do an experiment and I find that I get 5.1 milligrams of product, then this is a quantitative observation. So you'll notice that, if you perform an experiment several times, maybe it has a smell sometimes, so maybe that smell is more intense one time over another. So you can, compare and contrast qualitative observations there. And the same thing with quantitative too. Maybe on the second experiment trial, I don't get 5.1, maybe I get 5.0, or maybe I get 4.7, right? Different things like that. So those are the different types of observations. Now, how these observations build is essentially how you get the difference between a theory and a law. So theories are comprehensive, testable explanations of particular aspects of nature. Now, what's really important about theories is this point here. They can be modified and they can be changed if new data becomes available. So, in atomic theory, we used to, back in the time of Democritus, 600 BC or so, give or take, we just believed that atoms were circles and they're indivisible. That means they can't be split. They're just solid balls. And eventually, when they can't be cut anymore, that's how we get atoms, right? However, through experiments throughout the years with Rutherford and Bohr and Thomson and Millikan and different things like that, we have understood that atoms are not really the smallest thing. We know that we have subatomic particles. We have protons, we have neutrons, and we have electrons. And we know that they occupy different parts of the atom. So because this theory has kind of changed over time, or because these observations and explanations have changed over time, that's what's going to allude to a theory here. Laws, however, are basically just big summaries of consistent experimental evidence and experimental observations that scientists have seen. A good example of this is the law of conservation of mass. Basically, what's that saying is that when you do a chemical reaction, if you have some amount of mass before the reaction, you perform the reaction, you're going to have that same amount of mass at the end. It's simply just a rearrangement. So if I were to describe this in terms of observations, let's say I did 100 grams of reactant. What would I expect as my product? 100 grams. So this is a law because you can do this experiment over and over and over and over again. And as you replicate it many, many, many times, you're going to find that you achieve the same observation. You would say that your reactants, in this case I'll call them A, that's going to equal your products B. Okay, so this is just a good example of a law, and there's many laws. There's law of conservation of energy, there's laws of gravity that you've learned in previous science classes as well. So all of these can really be interwoven. Knowing the difference between a theory and a law is critical in the study of chemistry.